In this video, I want to go over internal energy. So let's say we have this system. Let's say we have this gas system inside of this piston. This gas system has a certain amount of internal energy. And the symbol we use to represent the internal energy of the system is capital U. So let's say that this system happens to have 10 joules of internal energy. So why does the system have 10 joules of internal energy? What contributes to this 10 joules of internal energy? Well, we know this gas system is made out of these atoms and these particles. So we know these atoms can move. They're moving. We know they're moving and bouncing around and etc. So therefore, if these gas particles have mass, they're atoms, so they have mass and they're moving with given velocities, then we know they have kinetic energy. And we know they're moving translationally, so therefore they have a certain amount of translational kinetic energy. And the higher translational kinetic energy these particles have, the faster they're moving, the higher the internal energy. So it's this translational kinetic energy that contributes to this internal energy. But there's more. There's more that contributes. For example, what if we have some diatomic atoms? Then we know these diatomic atoms can be rotating. And we know the faster they're rotating, the higher the internal energy of the system. We also know they can be vibrating. And also, the faster they're vibrating, the more internal energy the system has. But there are some other characteristics. For example, we know these atoms are made out of protons and electrons. And due to the arrangement of these electrons, give these atoms some energy in the form of electric potential energy. And that energy also contributes to the internal energy of the system. And there are some other factors, but again, the key point is it's these microscopic characteristics that contribute to the internal energy of the system. And something else really important to realize is that the internal energy of a system is proportional to the temperature of the system. If we raise the internal energy of the system, we raise the temperature of the system. They're proportional. So therefore, you might wonder, how do we raise the internal energy of the system? And there are two ways you can raise the internal energy of the system. One way is by adding heat to the system, and the symbol we use for heat is Q. So let's say originally the system had 10 joules of internal energy, but then we add in 5 joules of heat energy. Now how much internal energy does the system have? Well, now the system would have 15 joules of internal energy. And not just that, we know it has more internal energy. So therefore the temperature must have increased. And that makes sense. We add heat, we raise the internal energy, and we raise the temperature. That makes sense. Adding heat raises the temperature. However, there are other ways we can raise the internal energy. That's true. Heat is just one of the ways. Another way we can raise the internal energy is by doing work on the system. If we do work on the system, on this gas, if we compress this gas and we do some work on this gas, we can also raise the internal energy of this gas. Again, let's say that originally we had 10 joules of internal energy, but then we do 5 joules of work on this gas. Now the gas has 15 joules of internal energy. So therefore the internal energy has increased, so now the temperature has increased. And notice, this is not intuitive. Yeah, adding heat, raising the temperature, that makes sense. However, we can also do work on the system. If we do work on the system, that also raises the internal energy, and that also raises the temperature. So we can do work, we can compress this gas, and that would also raise the temperature. So again, that's not entirely intuitive, but again, there are those two ways we can raise the internal energy. We can do heat, we can add heat, or we can do work. And this is the essence of the first law of thermodynamics. The only way we can change internal energy is heat and work. Even though in reality, if you were to read a typical thermodynamics textbook, you would see that that's not true and it's a little more complex than that. But again, that's the basic principle. So again, let's do some examples. Let's say we have this system. And let's say it's 10 liters, and let's say, so there's 10 liters of volume in the system of these gas particles, and let's say it has 10 joules of internal energy. Well, again, we said we can change the internal energy by either adding heat or doing work. So again, if we have 10 joules of internal energy and we add 5 joules of heat, then again, now the system would have 15 joules of internal energy and the temperature would increase. But we know we can also do work on the system. And that will also increase the internal energy. So again, how do we do work on a system? Well, if you haven't taken physics, don't stress out about this too much. But essentially what you can do is whenever you have a system and you apply force over a distance, you're doing work. We know a force times a distance equals the work done. So therefore, if we applied a force on this gas over a distance, we did some work on this gas, and we could do work on this gas. So again, if we applied a force downward and therefore compressed this gas, we would do work on this gas. And again, let's say we did 5 joules of work. Let's say originally we had 10 joules of internal energy, but then we did 5 joules of work. Now we know the system would have 15 joules of internal energy. And again, we know we raised the internal energy, so we raised the temperature. And again, so the key point is, whenever you compress a gas, whenever you're compressing a gas and you're compressing and the volume is decreasing, you're doing work on the gas. Because again, you had to apply force to compress this gas. We know there's pressure, so therefore to compress this gas, we would need to apply a force over a distance. So therefore, when you compress gases, that's when you do work. That's when the system has gained internal energy. The internal energy increased when you compress a gas. And again, it's because we're doing a force over a distance. But in reality, because this is a 3D system, really what we're doing is there's a pressure and we're changing the volume. So at a given pressure, we're changing the volume from this volume to this volume. So therefore, we had a change in volume. We could see this much volume had changed. We could see about this much volume had changed. So therefore, what's important to note is if you know the pressure of the system and you know the change in volume, you know what the change in volume was, then therefore you can find out how much work you must have done. So again, based on what the pressure was and based on what this volume was, this change in volume that we saw, we could calculate that and we could see how much work we had done. And we said we did 5 joules of work. So the key point is when you compress a gas, you're doing work on the gas and the gas raises its internal energy. However, what if we went in the opposite direction? What if we decompressed a gas? Well, remember, when we compress a gas, the gas raises its internal energy. So when we decompress a gas, it loses some internal energy. So now its internal energy would maybe be 5 joules, and it lost internal energy. Because again, before in this situation, we were doing a force on the gas, we were doing work on the gas, applying a force over a distance. So we were doing work on the gas, so it gained energy. However, in this situation, the gas lost energy. Essentially, what happened was the gas was now doing work on the atmosphere. The gas was decompressing, so therefore applying a force upward, doing a force on the atmosphere. So it did work on the atmosphere, so therefore it lost that energy, and the atmosphere gained that energy. So now the system lost internal energy, and therefore we would see the temperature would decrease. And again, how do we find out how much internal energy it lost? Well, again, if we know the pressure times the change in volume, what this change in volume was, then we can determine how much work it lost and how much energy it lost. And again, in these situations, we're assuming that the pressure was constant, which kind of simplifies the math. But now let's talk about these PV diagrams. So these are common diagrams you'll see in physics and chemistry classes. So let's draw a PV diagram that represents this situation, where we did work on the gas. Well, in these PV diagrams, this axis represents the pressure, and this axis represents the volume. So again, we said originally we had 10 liters. So let's say we had a certain pressure. Let's say we were at 1 atmosphere pressure and we had a certain volume at 10 liters. So therefore, this original situation would be represented by this dot. But then we did work on the system. We did work and we compressed this gas, making its volume decreasing. We decreased its volume, so now its volume decreased to let's say 5 liters. So therefore, we know we did work on the system. So now the system has 5 liters of volume. So now we would be at this situation where the volume is at 5 liters. So this graph, what would happen, this change would be represented by a line going in this direction. We were originally here, now we're here. This original system was this, now we're here, now we're at this final situation. And something important to note is the volume underneath these PV diagrams, this volume underneath this line, represents the work that was done. Because again, we know work is pressure times the change in volume. If we have a pressure and we multiply by a change in volume, we get the work done. So again, we see we have a pressure and we're multiplying it by a change in volume. And that would be this area. But something important to note, remember, when the volume is decreasing, so therefore when we're going in this direction and the volume is decreasing, then this is the work that was done on the gas. This volume is the amount of work that was done on the gas, how much energy, internal energy, this gas gained. Because again, the volume is decreasing. When the volume is decreasing, so when we're going in this direction and the volume is decreasing, then we know we're compressing the gas, so we know this work represents the energy that that was done, the work that was done on this system. However, in this situation, when the volume is increasing, then we would see maybe originally if we were at 10 liters, but now the volume increased, the graph would look like this. We would go in this direction. So therefore, what does this work represent? What does this volume underneath this line represent? Well, again, in this situation, when the volume increases, when the volume is increasing, going in this direction and the volume is increasing, that's work that this system is losing. Because again, we said the system lost internal energy. So this is energy the system is losing. So now this area represents the energy that the system lost. This volume represents the work done, the energy that this system lost. So again, the point is, the area underneath the graph when the volume is decreasing represents the work that was done on the system. However, this area of the graph, underneath this graph, when the volume is increasing represents the work that the system lost. And that's what's going on in these PV diagrams.